Hi, I'm Ben-Yaakov. This presentation is entitled Answers to Analog Riddle Part 1, Current Transformer and Precision Rectifier. The riddle is posted at my YouTube channel. Here's the link. And the riddle is related to a description of a project which can be found at the Altium website. Here's the link again. So the riddle is pointing out to some mistakes in the description of the project, and here I'm giving some of the answer to the question, what are the mistakes? So let's first of all recall the questions that I've posed that I'm going to address in this presentation. Here it is. The purpose of this rectifier is to provide a positive or unipolar signal to be sampled by an A to D fed to a microcontroller, and this signal is representing actually the current passing through some circuit here, AC current. It's a line current, AC 50 or 60 hertz, and this is the current transformer. We have here a voltage which is the function of the current, proportional to the current, and the precision rectifier converts the bipolar sinusoidal waveform to a unipolar positive voltage, so that a conventional A to D converter can sample it without the need to sample a bipolar that is plus and minus voltages. So this is the purpose of this rectifier. The questions that I've posed were, what is the problem with this rectifier, or I should say problems, many problems that this rectifier has, which makes it to be not the best of the designs possible. So this is one of the questions. Another question was related to the transformer. This transformer is a commercial unit. Let's have a look at the number here. Here it is. This is the company, Talema, and it's AC 1010. This is an AC transformer, and my questions were related to the datasheet of this transformer. Okay, so here is the datasheet. This is this transformer. It's a 10 amp current transformer. This is the current transformer. The wire that the current of which is going to be measured is going through this hole here, and here are the outputs. This will be the configuration. Here's the input, here's the output, and you load it with a resistor. In this case, they are showing 100 ohms. Now, this again is an AC transformer, 50, 60 hertz. And my question were the following. First of all, looking at this plot here, we see the input current, we see the output voltage as a function of the load resistor. This is this resistor, and the question was, why is it that at low resistances this is sort of a straight line, and then it gets sort of corrupted and it sort of saturates? So why is this? This is first question. Second question was, looking at this is again the output current, this is the output voltage, this is for 100 ohms. We see here sort of a straight line, and then it sort of saturates here. And the question was, what's the reason for that? And the third question was, what are the parameters that are missing from this datasheet? This datasheet includes, you see, the current, the turns ratio, volts per amp for 100 ohm, but some parameters which are important for a designer are still missing here, and the question is, what are they? So let me first address the issues here of the current transformer. So what is a current transformer? Basically, it is a transformer which has a certain turns ratio, 1 to something, because we have one turn, which is the wire going through the transformer. In this particular case, it's 1 to 1,000. So if we have a current coming in, we have a current coming out, which is 1,000. This part here is sort of the ideal transformer, and this represents the magnetization inductance, and this is the leakage, which I'm going, in this case, now to sort of ignore, because this is just a general description of the problem. So we have a current coming in, we have a current coming out, and this current now is splitting between this path here through the resistor and the magnetization inductance. Now, if this path has a much lower impedance than this L sub m, then obviously most of the current will be passing through here, and then we'll have a V out equal to I in over 1000, this is the turns ratio, times R out. This is the output, and in this case, 100 ohm, we are getting 0.1 volt per amp, which is fine. But if Lm is low, that is, the impedance of Lm is low at a particular frequency we are talking about, and we are talking about low frequency, so omega Lm is small. So if this is not holding, but the reverse, that is, this is smaller than this, then most of the current will go this way, and obviously we're going to have a lower voltage at the output. So this explains the curve here, that at low impedance, low resistance, you have a straight line, and obviously the larger the resistance, the higher the voltage, like this will be twice this voltage. You see this is 1 and this is 2. And then it goes up, but eventually you have a lower voltage output, but also we see here some sort of saturation. We see the saturation also here, and the question is, what is the reason for this saturation? And the reason is that we have also here a BH curve. This is the core of the device, and we have a region in when B, that is the magnetic flux density, is reaching a maximum value of saturation, and therefore the voltage will not go up. Now the question is, what is the relationship between B and the voltage? So we look now at this simple expression. V out is N times the phi dt, and since phi is B over A times A, then we have V out N A dB dt. And now we're taking the integral here, V dt, and this is equal now to the maximum value over N times AE. AE is the cross-section area of the core times delta B. And I'm showing it here. This is the integral from 0 to pi, and here is the delta B going from the minus value to the plus value. So this delta B is related to the volt second. So once we reach this volt second, which depends on the voltage and the frequency, of course, because the integral here will depend on the value of the voltage and this time, and the lower the frequency, the longer the time, and the larger will be this value. So once we reach B max, we are going to sort of saturate. Now, in many data sheets of current transformer or transformer in general, you'll get this number, volt second, maximum volt second. This is the maximum volt second that brings you to B max. So this is definitely a missing parameter in this data sheet. Another missing parameter is the impedance here, or the inductance. If you know the inductance, then you can tell what should be the value of resistance or resistor that will be good enough in terms of the current going through it rather than through this Lm. And also you can figure out what happens at other frequencies. For example, if I like to use it at, say, 400 Hertz, which is the aviation line, then obviously I like to know what is Lm, and then I can calculate omega Lm and see if my resistor is indeed holding this relationship. So this explains the curves and also the missing parameter. So let's move now to the rectifier itself. So here is the precision rectifier. This is the transformer, AC coming in, and the voltage here is the current divided by 1000. This is the turns ratio. And then the operation of this precision rectifier can be explained as follows. We have here a voltage which is a sinusoidal voltage. Here, look at this. This is an inverting amplifier from here to here. So for the negative part of the sinusoidal waveform, we have here a positive voltage and therefore a positive voltage because we have a diode this direction. So a negative part becomes a positive part here, which is fed to this amplifier. Now when the voltage here is positive, it should have been negative voltage here, but due to the diode it's not conducting. So what happens is that actually we are now imposing a high voltage between the inputs, which should be of course virtual ground in the linear mode, but now we are pushing it hard actually in saturation. This will swing as low as it can. This is a single supply design, and this is a rail-to-rail amplifier. So this voltage will go down up to approximately ground, not exactly, but close to ground. It's depending on the amplifier, the type of amplifier. And in this case, this positive voltage now goes from here to here to here and to here. So we now are getting here the positive voltage itself. This is here the inverted negative voltage. So here we have a rectified voltage. So now we have another amplifier, which is just a follower with a gain. The gain is R8 plus R5 over R8. This is 15 over 5, so it's 3. And this waveform here is now rectified, coming out. Being a positive, the diode is conducting it, so we see it here. And then we have a filter which is sort of filtering out the high frequency noise perhaps. This filter is for, I guess, something like 600 hertz, and therefore it's the breakpoint is above the 50-60 hertz, so it really does not corrupt, or it's not supposed, I should say, to corrupt the waveform. So this is the principle of operation of this precision rectifier. And my question in the riddle was, what is wrong with this design, and how could it be fixed? So let's first of all concentrate in this presentation on what is wrong with this design. So let me start first of all with this source. Contrary perhaps to intuition, here it is not a voltage source, because we have a current coming into this resistor. So this is the model, current into the resistor, and the Thevenin equivalent, voltage equivalent, is a voltage source plus a series resistor. So this is a voltage plus a series resistor. So therefore, the resistance here is not 10K, but 10K plus 100, okay, 10K plus 100. And therefore, the gain here is not 1. Now, in the final design, these are supposed to be 0.1% resistors, so that the design will be, or the rectifier will be very accurate. Now, obviously, you have an error here. In fact, this error is 1%. That's 10 times the accuracy you want. So this is the first mistake here. This is not a voltage source. It is a voltage source with a series resistance. So therefore, you have to compensate for it either by reducing the resistance here or adding 100 ohm here if you want a 1-to-1 ratio. Okay? So this is the first problem for this claim to be precision rectifier. Now, let's go to the second point. As I've shown, here we're going to have the negative part inverted, the positive part coming here, so we have here only positive voltages. So therefore there is no need for a diode, because it's only positive voltages, and a direct connection would just provide these positive voltages to the output filter. Now in fact, I'll show you in a minute that this rectifier causes a big problem. And indeed, if you look at designs of many application notes, and I just brought an analog device case, and you see here this is very similar. There's small changes. I'm not going into the little details. There's no diode here. There's no need for a diode, because here we get a positive voltage, and therefore you get a positive voltage here, and it'll fit the output filter. But there's another issue here, and you see that here they've added a diode in this direction. That is, aside from the diode that is doing the rectification, and they take the output from this resistor because this is the gain here, this goes to the other direction. Why is that? Because without the diode, as I've said, the voltage here will go high during the positive half cycle, pushing the amplifier into hard saturation, and therefore you'll have a sort of a time of recovery when you go back. Now, depending on the amplifier, this particular amplifier is fairly fast recovery, but some others will have a slow recovery. So it is not recommended to push the amplifier hard by imposing a high voltage between the inputs, but rather to always have a feedback, so to keep the virtual ground, and this is done by the diode. So the diode is ensuring that the amplifier will be always in the linear region. Either it's amplifying here, or it is generating a negative voltage here, depending on the voltage drop of the diode, because here is ground, virtual ground, so this is ground, so this will be like a minus 0.7 volt. But with a single supply, you can't have it. So in this case, you really can't put a diode. I'm going to show later on that you can have a offset that will then allow the use of a diode. Now, you can then subtract this offset by the microcontroller that is reading the A to D, because this is going to be read by a digital controller, and therefore everything will be positive, but will be riding on a certain offset, and this offset can be then subtracted, and it will allow to put the diode. So I'm going to show it in my next video on the subject. So this is another issue here, that there is no diode in the original design, and it's really highly recommended to have a diode. And then we come to the filter point. Now, this filter is now fed from this amplifier, but with the diode, which is not needed, but it's given here. Now, during the time that the waveform is sort of riding up the positive slope, the diode is conducting, charging the capacitor. Now, what happens as the voltage goes down? In this case, the capacitor has to be discharged. Now, if this would have been connected directly, it could have discharged into the amplifier. It would sink, the amplifier would sink this current. So this would be a linear filter. Now, because of the diode, the current has to go this way. So this is now a nonlinear filter, because it's one way, one time constant, the other way it's another time constant. So therefore, rather than getting at the output a nice waveform, you'll get something like that, because here it's sort of depending on the discharge, RC discharge here, rather than the controlled current sinking of the amplifier that would cause this to follow the exact required waveform. So in this case, this is causing a error. And indeed, if you look up at the waveform that are shown in the project description, you see this. And that's exactly it. Going up, everything is fine because the amplifier is pushing the current through the diode into the capacitor. And then here you rely on the discharge of the RC, which with a much larger time constant that this causes this thing. So this is another problem. So let me just summarize. We have, in this case, we have the problem of this being a current source, so these resistors are incorrect, that you have to do some changes, other subtracting here or adding here 100 ohm. We have the problem of pushing this transistor, this amplifier hard into saturation, and then we have the recovery, although this may not be a big problem if the frequency here is low, but if it would have been a high frequency, this could be a big problem. And then we have the diode, which is really not needed, and then we have the nonlinear filter here, which causing a distortion due to the fact that the capacitor is not discharged in a controlled way by the amplifier, rather by a RC circuit, which with a time constant which is much larger than the original filter. So this actually ends part one. This is only part of the answers because there have been many points that I've raised of this project description. And this brings me to the end of this presentation. I thank you very much for your attention. I hope you found it interesting and perhaps it will be useful to you in the future. Thank you very much.